Welcome back to the deep dive. Today we're doing something a little different.
Yeah, we are.
Usually we sit here and we talk about the user experience, how to talk to an AI, how to prompt it, how to get the best answers out of it. We tend to look at the shiny surface of the
The
technology.
front end?
Front end, exactly. But
Right.
today we are shifting seats. We are moving to the other side of the
We're
table.
putting on the hard hats today.
Exactly. We are looking at you, the listener, right now and saying, today, you are the architect. Because look, everyone is talking about chatting with AI.
Hmm.
My grandma talks to ChatGPT. My nephew uses it for homework. That's the surface level.
That's consumption.
It is. But the real engineering challenge, the thing that keeps CTOs, lead developers, and enterprise architects up at night, is building systems that actually do work.
It is the difference between a magic trick and a machine. A magic trick is cool once, at a party. It surprises you, delights you for a second. But
A machine has to run.
a machine has to run 24/7. It has to be reliable, scalable, safe, and most importantly, predictable. And to do that, you can't just rely on a clever prompt. You can't just wish for the best.
No.
You have to think about system architecture.
Right. So consider this your masterclass in architecting the agent. We are going to visualize the invisible loops that make these things run. We are not talking about prompt engineering today, not at all.
No, this is plumbing.
We are talking about the plumbing, the wiring, the agent loop, and the RAG pipeline.
And we are pulling this from a pretty serious stack of technical scenarios. We've got insights ranging from intermediate integration patterns, like how do you hook an AI up to a SQL database safely, all the way to expert-level deployment strategies, specifically for the Google Cloud stack.
So we're talking Vertex AI, Gemini.
Exactly. Vertex AI, Gemini, the React framework, and how it all fits in with the open source ecosystem. This is for the builder.
So if you're ready to build, here is the roadmap. We have 4 main pillars to get through to make you a certified agent architect.
Right. And it's a logical flow. First, we're going to look at the brain. This is the React framework. It's how the agent thinks. It's how we move from a simple text generator to a real reasoning engine.
Then we move to the hands, because a brain is useless if it can't do anything. This is about tools and function calling. How does the AI actually touch your API or your database?
Third, we tackle the memory.
Oh.
This is a big buzzword. RAG. Retrieval Augmented Generation. I mean, how do we give the AI a library to reference so it doesn't just hallucinate or make things up?
That feels like the most important part sometimes.
It's critical. And finally, we wrap it up with the strategy, the hybrid future. Do you go open source? Do you go proprietary? How do you even begin to decide? We've got a decision matrix for that.
The brain, the hands, the memory, and the strategy.
It's the full stack.
It really is.
Yeah.
So let's dive into pillar 1, the brain, specifically something called the React framework. Now unpack this for me, because to most people, an LLM, a large language model, is just a text predictor. It's essentially fancy autocomplete.
That is exactly what a base model is.
Uh.
I mean, if you strip away all the marketing, a model like GPT-4 or Gemini is fundamentally a statistical engine.
Right.
It predicts the next word based on probability. It reads, the cat sat on the... and it predicts Matt. It doesn't know what a cat is. It doesn't understand physics or gravity. It just knows that in the billions of sentences it has read, Matt is a very high probability word to follow that sequence.
So it's strictly linear. Input goes in, a string of text comes out, but an agent feels different. An agent feels like it has a goal. It feels like it's trying to achieve something, not just talk at me.
And that's the core distinction. You've nailed it. An agent is defined by its ability to reason and execute a specific workflow.
Or workflow. Okay.
It's not just generating text. It's actively trying to solve a problem.
Yeah.
And the engine that drives that problem solving, the methodology that turns a text predictor into a problem solver, is the React loop.
React, R-E-A-C-T. What's that stand for?
Right. It stands for reasoning in action. It's a
Like-
conceptual framework that turns the linear model into a loop, a cycle.
Yeah.
Instead of just input-output. The cycle, as described in all our sources, goes like this. Observe, reason, decide, act.
Observe, reason, decide, act.
Okay. That sounds very logical, almost like a military OD, loop, observe, orient, decide, act.
It's very similar in spirit.
But let's make it concrete. I know you have an analogy for this because these abstract loops can get a little heady for people just listening in.
I do. I want you to imagine a chef, a really good one, in a high-end kitchen.
Okay, I'm picturing a chef, high white hat, maybe a little stressed, bubbling pot on the stove, smelling the aromas.
Perfect. Now, a standard text predictor, LLM, is like a person who has read a million cookbooks but has never actually cooked a meal in their life. They
Okay.
have a perfect recall. If you say, how do I make a perfect tomato soup? They will recite the text from the book flawlessly.
Yeah.
But if they're actually standing at the stove and the soup is bubbling over or it tastes way too salty, they don't know what to do. Because they're just reciting text. They aren't in the loop of reality.
Exactly. They are theoretical chefs. They can describe the soup, but they can't fix the soup that's right in front of them. Now, the React agent is the chef who is actually cooking. They are interacting with the environment. They're dynamic.
Okay, so walk me through the React loop using this chef. Let's say the goal is to make a perfectly balanced soup.
Okay, step one, observe. The chef leans over the pot. They look at it, they smell it, and crucially, they taste the soup. That's the input. They are gathering real-time data from the actual environment.
So it's not data from a cookbook they read 3 years ago, it's data from right now, this second.
Exactly. This is the observation. Step two, reason. The chef thinks, and in the AI world, this is literally an internal monologue, a thought trace generated by the model for you to see. They think, this tastes flat, it's one-dimensional, it lacks depth, it needs some kind of balance.
That's the reasoning step. Okay. So they are analyzing the observation. They are applying logic or, I guess, taste to the sensory input.
Correct. Step three, decide. The chef decides, I should add salt. That's the intent. They have formulated a plan based on their reasoning. The thought leads to a concrete plan of action.
And step 4, act.
The chef physically picks up the salt shaker and adds a pinch of salt. This is the action. In AI terms, this is calling a tool. But here is the critical part. The part that separates a real agent from a hallucinating chatbot. What happens after the chef adds the salt?
Well, if it was a bad chatbot or just a basic text generator, it would probably just say, I added the salt, here is your soup, enjoy.
Right. A bad bot would just confidently declare, I added salt, it is now delicious. But the bot doesn't know that. It has no idea. The lid could have fallen off the shaker and a pound of salt went in. The salt could have been sugar by mistake. The bot has no idea what the actual outcome of that action was.
So the chef has to loop back. They can't just serve it. That's malpractice.
Exactly. They have to loop back to the very beginning. Step one, observe. They taste the soup again. This is the feedback signal. Then they reason again. Okay, that's better on the salt, but now it needs a little heat, a bit of chili flake. This loop think, act, observe, think, is the absolute heartbeat of a true agent. It allows the system to self-correct and iterate towards a goal.
That observe step seems to be the one that I think technical people miss when they are first building these things. They focus so much on the act.
It is the most crucial step, and it is absolutely the most neglected. In the technical documentation we have, there is a specific, bold-faced emphasis on this. It states that after a model acts, which in software terms usually means calling a tool or an API, it must receive an observation.
So mechanically, let's look at the code for a second. The model sends a command like add salt, and then it literally stops. It just waits.
Yes. It pauses execution. The control loop holds the state. The tool runs. Maybe it queries a database. Maybe it checks the weather. Maybe it executes a trade. And the tool sends back a result. The salt was added successfully.
Oh.
Or error. Salt shaker is empty. That result is the observation.
I see.
Only then does the model wake up and say, I see the result. The salt was added. Now I will taste again. Or, the shaker is empty. I will now form a new plan to find more salt.
If you skip the observation, you're just guessing. You're flying blind.
You are hallucinating. You are the chef serving soup you haven't tasted. You are just hoping it worked, but you haven't verified it. And in an enterprise setting, hope is not a strategy. You'll get fired for that.
And there's another component mentioned in the source called the control loop. Because if the chef just keeps tasting and salting and tasting and adding chili, they will never actually serve the soup. They'll just be stuck in the kitchen forever.
Right. And this is a key architectural point. The model itself, the neural network, is just the brain tissue. The control loop is the skull. It's the code that wraps around the model and says, okay, keep looping. But it also monitors the state. It's the thing that decides when to stop.
It needs a definition of done, a stopping condition.
Exactly. It is goal-directed. The source detail mentions that this component is responsible for deciding when the answer is good enough to return to the user. The chef thinks. The soup is now perfectly balanced. The seasoning is spot on. That is the termination signal. The control loop sees that and says, okay, goal achieved, serve the soup.
Or, conversely, I have tried to fix the soup 10 times and it's still bad.
Throw it out.
Right.
That's error handling. The control loop prevents infinite loops. It manages the budget of the agent's attention, the token count, the API costs. It's the governor on the engine.
So when we talk about architecting the agent, we aren't just picking a model from a drop-down menu. We are building this entire harness around it. The loop, the observation mechanism, the stopping criteria, the error handling.
Precisely. You're building a system that allows the intelligence to iterate safely and effectively. Without the loop, it's just a rambling stream of consciousness. With the loop, it's a problem solver.
Okay, so we have a brain that can think in loops. It can reason and act. But like you said, a brain in a jar isn't very useful. It can't affect the real world. It needs to touch things. It needs hands.
Which brings us to our second segment, breaking the glass tools and function calling.
Yeah, the brain in a jar problem is the classic limitation of Gen AI. A base model, like Gemini or GPT, is completely isolated. It lives on a server in a data center somewhere. It has no idea what time it is right now.
No clue.
It doesn't know what the stock market is doing this second. And it certainly can't look into your private company database to see if your order has shipped.
It's frozen in time from whatever it was last trained. So if
Yeah.
I ask it, where's my package? And I ordered it this morning.
The model has no idea you even exist. It knows about packages in general. It knows FedEx exists. It knows what tracking numbers are conceptually, but it doesn't know anything about your package. So how do we break the glass? How do we give it hands to reach out and grab that tracking number from the real world?
We use tools. In the developer world, this is often called function calling.
I love the term function calling because it sounds very technical, very, deep computer science. But when you break it down, it's actually really intuitive. It's just giving the AI a menu of things it's allowed to do, right?
That's a great way to put it. Imagine you are the architect. You are briefing your new AI agent. You tell it, hey, you are a customer service agent. You can chat about the weather. You can be polite. But then you also have a special red button on your desk called Check Order Status.
And we write a little description for the AI. If the user asks about a package and you have their order number, press this button.
Exactly. But here is the magic and where the architecture comes in. The AI doesn't actually go into the warehouse. It doesn't drive the truck. When it presses the button, it generates a specific structured piece of text, usually it's a JSON object, that contains the data needed. Something like tool name, check order status, parameters, order ID 12345.
So it's not performing the action itself, it's just filling out a form, a request form.
It fills out a digital form. And then that form is sent to a piece of code that you, the architect, have written and control. The AI isn't running the code, it's requesting that your code be run on its behalf. This is a critical safety boundary.
Let's look at a scenario from our source stack. We have a customer-facing agent, and a user asks, where is my package?
Okay, so the AI, the brain, analyzes that text. It reasons in its internal monologue. The user is asking for their package status. My instructions say I should use the check order status tool for this. It then decides to call that tool, and it acts by outputting that JSON function call we just talked about.
Now, architecturally, what handles that? Where does that JSON object go?
The source mentions something about lightweight, event-driven functions.
Right.
Yes. For a simple, stateless task like checking a status, the architecture often uses something like cloud functions.
Cloud function. So that's like a little serverless script. It just exists and waits to be called.
Exactly. It's a tiny piece of code living in the cloud that does one thing and one thing only. It wakes up when that JSON object arrives, it parses it, takes the order ID, it hits the real shipping API like FedEx or UPS. It gets the data back. Your package is currently in Toledo, and it returns that text string back to the AI. Then it shuts down, and you stop paying for it.
So the full flow is user asks question, agent reasons. Agent calls function. Your cloud function gets triggered. Cloud function hits the real-world API. Cloud function returns the answer, Toledo, to the agent and then answers the user.
Perfect. And that return value, that simple string Toledo, that is the observation we talked about in the React loop. The agent receives packages in Toledo as an observation. It then reasons, okay, I have the location, I should now tell the user in a friendly way. And finally, it acts by generating the response for the user. Good news, I've just checked, and your package is currently in Toledo.
So the AI didn't know where the package was, it knew how to ask.
That is the fundamental shift in thinking for an architect. We are moving from knowledge retrieval, what the AI memorized during its training, to tool use. What can the AI do right now?
And this gets more complex. I mean, one of our sources describes an agent executing a SQL lookup in a database to find a customer's entire order history.
Yes.
Whoa, wait, writing SQL, that sounds really dangerous. I mean, if the AI hallucinates bad SQL, could it delete the database or expose data it shouldn't, drop table users?
That is a very, very real risk, and that's why the tool definition is so important. You typically don't give the AI root access to the database. You don't just say, here's the database connection string, write whatever SQL you want.
That would be insane. That's a fireable
It
offense.
would be professional negligence. Instead, you build a tool. It's actually as a safe wrapper.
Hmm.
The tool is named Lookup Order History. Its description says, use this to get the order history for a customer. The AI just provides the customer ID. The tool itself contains the pre-written, sanitized, safe SQL query that has been vetted by your engineers.
Ah, okay. So the AI is just filling in the variable on a template. Run the pre-approved order history query for user 123.
Exactly. It's much safer.
Yeah.
But it still counts as an action.
Hmm.
And this is a really important distinction. This is distinct from RAG, which we'll get to, which is just reading information. This is doing something. It's an active process.
Now, what happens when the conversation gets messy? Because humans are messy. Like, say I'm ordering a cake. I tell the bot, I want a chocolate cake, but I didn't say what size, or when I want it delivered, or where to deliver it to.
This is a classic problem in conversational AI called state management, or more commonly slot filling.
Slot filling, like filling in the blanks on a form.
Exactly. The source material gives us the bakery chatbot scenario. To place a successful cake order, the bakery's API needs 3 variables, or slots, to be filled: flavor, size, and address. You cannot proceed without them. The API will just reject the order if any of those are missing.
So if I just say chocolate, the AI has to realize, okay, I have the flavor slot filled, but I'm missing the size and address slots.
Correct. And it needs to loop back and ask specifically for those missing pieces. Great, chocolate sounds delicious. What size would you like for that? And after you answer, and what address should we deliver it to?
Now, can a regular LLM in a React loop do this?
It can, but it can be flaky sometimes. It might get distracted. You say chocolate, and it might start talking about the history of chocolate in Mesoamerica. It might forget that you still haven't given the address yet. For complex, multi-turn flows where you must gather specific data reliably, our sources point to more specialized services, like Dialogflow CX.
Dialogflow CX, why would I use that instead of just a raw LLM agent? What's the trade-off?
Because it is state-based. You can visually build the conversation as a flowchart. You can define a state called collecting order details, and you can set a rigid rule on that state. Do not leave this state until the slots for flavor, size, and address are all full.
It's a guardrail, a very strict one.
It's a very strong guardrail. It combines the natural language flexibility of an AI conversation, so it understands, I want a dark chocolate delight for about 10 people, with the strict logic of a business process, which is, I absolutely must have the size before I can proceed.
So for the architect listening, if you need strict rules, like a bank authentication process or a pizza order where you have to get the address right, you might want to look at a state machine like Dialogflow. If you just need a creative brainstorming partner, maybe a raw agent is fine.
Exactly. It's about picking the right tool for the level of stability and reliability you need for that specific task.
Okay, so we have the brain react and the hands tools.
Yeah.
But an agent that can think and act is still pretty useless if it has amnesia or if it doesn't know anything about my business. I don't want it to just know what's on the public internet. I want it to know about my company's specific HR policies or our internal technical manuals.
And this brings us to the infinite library. This is the third pillar, RA.
Retrieval Augmented Generation. I feel like this acronym is tattooed on every developer's forehead right now. It is everywhere.
It is the standard for a very good reason. The context problem is probably the biggest hurdle in Gen AI right now. The model has a limited context window. It can only hold so much information in its working memory at once. You can't just copy and paste your entire company intranet into the prompt.
It wouldn't fit. And it would cost a fortune in tokens.
It would cost a fortune.
Yeah.
And the model was trained months or even years ago. It doesn't know about the new product you launched last week or the memo the CEO sent this morning.
Correct. So we need a way to fetch only the relevant information, the specific page of the manual, the specific email, and feed it to the brain right when it's needed, just in time.
That's our Reggie in a nutshell.
How do we do that? I mean, how do we find the needle in the haystack of all that corporate data? We've had search bars for years, and they're usually terrible.
They are, because they rely on keywords. RG relies on something different. It's a process involving embeddings and vector search.
Okay, let's unpack embeddings, because that sounds like math. And we promised the listener we'd visualize this, not give them a linear algebra lesson.
It is math. It's very high-dimensional linear algebra, but we can absolutely visualize it as a map, a giant two-dimensional map of meaning. Imagine that every single word and concept in the English language has a specific GPS coordinate on this map based on its meaning.
Okay, I'm picturing a huge world map.
So on this map, where is the word apple?
Well, that's the classic question. It depends. Are we talking about the fruit or the tech company?
Exactly. And that is the problem with old-school keyword search. If you search for apple, you get both, and it's a mess. But on our semantic map, our vector space apple, the fruit is located on a continent with banana, pear, pie, and snack.
Okay. It's the food continent.
We can call it that. But Apple, the tech company, is located on a totally different continent, thousands of miles away, right next to Microsoft Computer, iPhone, and stock market.
So the system understands context because these two identical words live in completely different conceptual neighborhoods.
Precisely. This is semantic search. It understands intent. It understands meaning. If you search for a delicious red snack, a keyword search might fail because the word apple isn't in that exact phrase. But the vector search looks at the GPS coordinates of delicious red snack and sees that the coordinate for apple is sitting right next to it on the map. It's a close neighbor.
That is a total game changer. It means you don't have to guess the exact keywords the author of a document used. You can just ask a question in natural language.
You can. So for the architect, how do you build this? The source material points to a specific component in the Google stack designed for this: Vertex AI Search and Conversation Data Store.
Vertex AI Search, that's a mouthful. What does it actually do under the hood?
It manages the entire RAG pipeline for you, because you can't just throw 1,000 PDFs at a map and hope for the best. The source mentions the prerequisite setup phase involves two key steps: chunking and indexing.
Walk us through that pipeline. Let's say you have 100 employee handbook PDFs.
Okay, you have a mountain of PDFs. Employee handbooks, technical wikis, marketing one-pagers. First, the system chunks them. It breaks these long documents into small, bite-sized paragraphs or sections, because you can't feed a whole 300-page book to the LLM easily. You want to find the specific paragraph about paternity leave, not the whole chapter on benefits.
So chunking strategy matters. Too big and it's not specific, too small and you lose context.
It's a tuning parameter, absolutely. So now you have a million little chunks of text. Then you index them. The system runs each of those chunks through an embedding model, which turns each paragraph into a set of coordinates, a vector on that map we talked about, then stores these coordinates in a specialized vector database.
So now, when I asked a question...
When you ask, how many weeks of leave do I get for a new baby? The system first turns your question itself into a set of coordinates. Then it goes to the vector database and says, find me the 5 or 10 chunks of text whose coordinates are mathematically closest to the coordinates of this question.
It finds the nearest neighbors on the map.
It finds the nearest neighbors, it retrieves them, and it feeds only those chunks into the brain, the LLM, as context.
And then the brain is instructed to answer the question using only that provided information.
Yes. And this leads to the critical concept of grounding.
Grounding, this is all about trust, right? Preventing the AI from just lying to you.
It's about anchoring the AI to a specific source of truth. If you just ask a generic AI, what is our leave policy? It might make up a plausible sounding but completely wrong answer based on what it read on the internet about generic American companies. But if you use grounding with Vertex AI Search, the prompt to the model is essentially, answer the user's question. By the way, here are 3 paragraphs of the official company handbook. You are only allowed to use the context provided below to formulate your answer.
It's like an open book test where you are only allowed to use the official textbook and nothing else.
Exactly. And the source mentions the importance of citations. An enterprise wants to search this unstructured data and provide answers with citations. Here is the policy on paternity leave, and I found it on page 12 of the 2024 HR Handbook PDF. Vertex AI Search is designed to do exactly that, to trace the answer back to the source chunk.
That is absolutely crucial for trust. If the bot can't tell me where it found the information, I can't trust it, especially in a regulated industry.
Especially in healthcare or finance. One of our sources mentions a healthcare organization using this to extract structured data from unstructured clinical notes. You cannot guess there. You need document AI to parse the forms and grounded search to find the facts. The stakes are just too high for creativity.
Okay, so we've built a brain that loops, React. We've given it hands to touch external systems, tools. And we've given it a near infinite memory that understands meaning, our rage. Now comes the really hard part, the decision-making, the strategy.
Right, segment 4, the hybrid architectures.
We have so many choices now. We have the big, fancy, proprietary models like Gemini, and then we have this absolute explosion of open source models, Llama, Mistral, Gemma from Google itself. How does an architect even begin to choose? It feels overwhelming.
The source material gives us a pretty clear decision matrix. And to make it simple, I like to use the analogy of a car versus a taxi.
Okay, I like analogies. Car versus taxi. Let's hear it.
Proprietary models, like Gemini Pro or Gemini Ultra, are like taking a taxi.
Okay. You get in, you tell it where you want to go, and it takes you there. Simple.
Right. It's fast, it's comfortable, it's integrated. You don't have to worry about the engine or changing the oil or if the tires are inflated. The driver, in this case Google, handles all of that for you. If you want native integration, like, say, you want your AI to work seamlessly with Google Workspace, or you want the absolute fastest inference speeds managed by Google's infrastructure, the source says, use Gemini. It's the taxi. It's optimized for the roads it drives on.
But you don't own the taxi. You can't tune the engine. You can't paint it purple. You can't see how it works inside.
Exactly. That brings us to open source, like Llama or Mistral. This is like building and owning your own car.
You have total control.
Total control, but also total responsibility. You have to maintain it.
Right.
You have to host it. You have to secure it. So why would you do this? The source material highlights a very specific intermediate to expert scenario. It asks, what if a research team needs to inspect and modify the model's internal structure, its weights for research and governance purposes?
You can't call up the taxi company and ask them to let you dismantle the engine of the cab.
No, you can't. Proprietary models like Gemini or GPT-4 are black boxes. You can't see the weights, you can't see the math inside. You just get an API endpoint. So if your primary constraint is architectural transparency or the ability to modify the training loops, you must choose open source. There is no other option.
And Google's strategy here is interesting because usually big tech companies want you to use their stuff end to end, but the source mentions an open ecosystem.
It's a very deliberate and, I think, smart play. Google isn't saying Gemini only. They are saying Vertex AI is the platform for all models. They have something called the Model Garden.
The Model Garden sounds peaceful.
It's basically an app store for AI models. You can go in there and with a few clicks deploy Llama or Mistral or Google's own open model, Gemma. You click a button and it runs on Google's optimized hardware on their chips.
So they are providing the garage for you to build and run your car in.
Exactly. They want the compute revenue. They want you running that open source model on their Vertex AI infrastructure. They don't care if you drive a Ford or a Ferrari, as long as you rent their garage and buy their gas. It minimizes vendor lock-in for the customer.
Let's talk about money, because architecting isn't just about code, it's about budget and business value.
Yeah, the source brings up the startup scenario. A startup with a very tight budget needs a simple customer service assistant. Do they use the biggest, baddest, most expensive model?
The source says absolutely not.
No. The critical consideration here is the price-to-performance balance. You don't take a Ferrari to the grocery store. You don't need the frontier model for a simple task like summarizing emails or answering basic FAQs. You might use a much smaller, cheaper open-source model or a flash version of Gemini that's optimized for speed and cost.
But then you flip that on its head. What about the mission-critical scenario? The source mentions an e-commerce company that's using an AI to forecast system failures in real time.
Right. If your system predicts outages, and an outage costs your company millions of dollars per minute, do you care about saving a few pennies on the model inference cost?
No, not at all. You care that it works. You care that it never, ever goes down.
Right. The priority there is high availability and an SLA service level agreement. You pay the premium for the guarantee that the service will be up 99.99% of the time. You pay for the taxi because if the taxi breaks down, the taxi company sends another one immediately. If your own custom-built car breaks down on the highway while you're walking.
So the lesson for the architect is, don't just pick the best model on some leaderboard. Pick the model that fits the specific risk profile and the budget of the specific use case you're building for.
Context is king. There is no such thing as one model to rule them all. It's a hybrid world. You'll use different models for different jobs.
Okay, we've covered the theory, we've covered the individual components. Now I want to put you to the test. Let's bring it all together. Segment 5, the expert final exam.
Let's do it. I'm ready.
We have a complex scenario from the source material. It's the global bank financial advisor. This is the ultimate boss battle of enterprise AI architecture.
I remember this one. It's great because it combines everything we've just discussed into one coherent system.
Here are the requirements. Listen carefully.
The bot must be able to answer complex client questions using the bank's proprietary market research, thousands of constantly changing PDFs.
It must never lie or make things up. No hallucinations allowed. If it doesn't know the answer, it must say so explicitly. And requirement 3. If the user gives explicit confirmation, it must actually execute a stock trade through the bank's systems.
Okay, this is a classic composite architecture. It's not one thing, it's a system. We need to combine the brain, the memory, and the hands. Let's build it layer by layer, starting with the hardest part.
Where do we start?
We start with the memory, those proprietary PDFs. We can't fine-tune or retrain a huge model on them because they change every single day, and training takes weeks. So we need RAG.
Okay, so we're going to use Vertex AI Search.
Yes. We build a process to ingest those new PDFs every day into a Vertex AI Search data store. And we make sure to enable grounding. This is the mechanism that ensures when the user asks, what is the bank's outlook on the tech sector? The answer comes strictly from those PDFs, not from the model's vague memory of the internet from 2 years ago.
So that satisfies requirement 1, use PDFs, and requirement 2, no hallucinations. The grounding keeps it honest.
Correct. Memory and truth are solved. Now, what about the brain that sits on top of that?
The brain.
For a complex financial conversation, you need a very capable reasoner. You need a model that can understand nuance, track a multi-turn conversation, and synthesize information from multiple documents. So we pick a strong, reliable proprietary model, like Gemini Pro. It's the taxi. It's powerful, it's managed, and it's good at complex reasoning. It will handle the conversation flow.
And finally, the action, the scary part. Requirement 3, execute the trade.
The brain, Gemini, cannot trade stocks. It's just a text engine. It can say, I want to buy stock, but it can't actually press the button on the trading desk. So we give it tools. We define a function called execute trade. The function definition will specify that it requires 3 parameters: ticker symbol, quantity, and trade type, buy or sell.
So when the user says, okay, after all that, buy 100 shares of Alphabet, what happens?
The brain, Gemini, reasons. The user has given a clear instruction to buy. I have the symbol, GOGL, and the quantity, 100. I will now call the execute trade tool. It then acts, outputting the JSON function call. The architecture, the control loop, routes that to a secure backend service, probably a hardened cloud function, which then connects to the bank's internal audited trading API, executes the trade, and returns a confirmation number.
And that confirmation number is the observation that goes back to the model.
Precisely. The model observes, trade successful, confirmation ID 98765. It then reasons, I should inform the user, and generates the final response. Your trade has been executed. Your confirmation number is 98765.
So the final architecture is Vertex AI Search for the PDFs, feeding grounded context into Gemini Pro, the brain, which is equipped with function calling, the hands, to securely execute the trade.
That is the composite architecture. It's not just asking a bot. It's a system of loops and integrations and safety checks.
It's impressive. It sounds solid, and there is always a but in these deep dives. Building the tech is only half the battle, maybe even less.
Oh, maybe less than half, yeah.
We have to talk about the organization. Let's go to our final segment, the outro, the reality check.
The source material has a very specific and, I think, very wise warning about something called the demo trap.
The demo trap. Oh, I've seen this a million times. A team builds a cool demo in a weekend hackathon. Everyone claps. The CEO is excited. Look, he can write a poem about our company. And then nothing happens. It never becomes a real product.
Right. 6 months later, 0 business value has been created. The source describes a CEO who is incredibly frustrated because their internal AI center of excellence is just making toys. They aren't shipping anything that moves the needle.
So what is the fix? What does the source say is the expert move here to avoid that trap?
You have to move from a skunkworks prototype to a funded cross-functional delivery team. And every word there is important.
Okay, break that down for us.
Funded means it has a real budget, not just the spare time of a few passionate engineers. Cross-functional means it's not just data scientists in a corner. It's product managers, designers, and, crucially, legal and compliance.
Legal is huge. You can't build a banking bot without them.
Especially for a bank. They have to be in the room from day one. And delivery team means their job, their performance metric, is to get it into production and create value, not just to make it look cool in a PowerPoint.
And the source also says you need to focus on a single high-impact pilot.
Yes. Don't try to boil the ocean. Don't try to AIFI everything at once. Pick one high-value, achievable use case, like that bank advisor for high-net-worth clients, and define clear KPIs for it.
Speaking of KPIs, the source had a great point about measuring success. If you build a coding assistant for your own internal developers, how do you measure if it's actually working?
It's not about model perplexity or some other technical jargon like that. The CEO doesn't care about perplexity. The source says the metric is reduction in time spent on writing boilerplate code or increased developer velocity. It's a business metric. Did we ship the new feature faster because of this tool? Yes or no?
I love that. Measure the outcome, not the technical output.
Exactly. That's how you get more funding for the next project.
So we've unpacked the React brain, the tool using hands, the ARG memory, and the hybrid strategy. We've built the bank advisor. We've hopefully avoided the demo trap.
We've covered a lot of ground today, a whole architecture.
We have. And I think the final takeaway for me is clear. The difference between a chatbot and a real AI application is this architecture. It's the loops, it's the grounding, it's the safe, reliable connections to the real world.
It's the difference between a toy and a tool, a real industrial-grade tool.
But before we go, I have one final question for you, a provocative thought to leave our listeners, our architects with.
Let's hear it.
We talked a lot about the agent loop, the chef tasting the soup, the idea of the observer. Right now, we, the humans, the engineers, are coding that observer role. We are telling the AI to check its own work, to observe the results of its actions.
Right. We build the feedback mechanism.
But as these agents get more and more autonomous executing trades, reading our emails, booking our flights, running parts of our businesses, who is watching the agent?
That is the big question, isn't it? The governance question.
As we build these increasingly complex loops, where does that observer role shift from being a line of code back to being a human? At what point do we become the observer in the loop, just watching the agents cook?
That's a little terrifying. But it's also incredibly exciting. I think it means our role as architects and developers fundamentally shifts. It shifts from doing the work to auditing the work. We become the head chef. We don't stir every pot anymore. We don't chop all the onions. We design the kitchen, we write the recipes, and then we just taste the final soup before it goes out to the dining room.
We are the head chef. I like that. Let's just hope the soup is good.
Fingers crossed.
Thanks for listening to The Deep Dive. Go build something amazing. We'll see you next time.